circle facts that are true, and then we can use them in algebra and proofs. So here's the first one. Let's get the first one. In that first diagram, can you put a center for me, please? Put a center right in that circle in the first theorem. All right, I'm going to use some vocabulary. Hopefully we're good. From that center, please draw it. Call that circle O, by the way, circle O. Sorry if somebody of you guys named it something else, circle O. Draw me an inscribed, draw me a central angle coming from that center, please. A central angle. Hopefully we know what I'm talking about. Draw a central angle coming from center O and call the other points A and B. So you have everyone should have one central angle in this circle that's named AOB. Next up, draw a second central angle in that diagram, please. Draw a second central angle. You either draw 2 more radii or you draw 1 more to make a second angle. All right, it's up to you. All right, draw a second. So you should now have 2 central angles. And name that other one with a C, D, or just C if you just drew in 1. All right, I'm just going to draw. You could draw in another one and make that. That's fine. Show me they're congruent. Show me those 2 central angles are congruent by putting, I know it's been a couple units, but what do you put on angles to show they're congruent? Arc marks, yep. So please put arc marks on your 2 central angles that you have drawn in. And here's the first fact for today. If you have 2 central angles in a circle that are congruent, so are the arcs. Okay, if the central angles are congruent, so are the arcs. And just so you know, notation-wise, if you ever want to show arcs are congruent, you do the same way we do segments, which are what? Hash marks, all right? So in this case here, if the central angles are equal, for me, so is arc AB and arc CB, but please use the letters that you use. And again, the way we can mark arcs congruent is with hash marks. So before I move on to the next fact, here's what it says again. If the central angles are congruent, so are the arcs. And the reverse is true. I just don't want to draw another diagram. If the arcs are equal, so are the central angles. All right, everyone good? Arcs are equal, central angles equal, so are the arcs. Any issues or comments on number 1? All right, let's roll. Number 2. Draw me a center again, please. Center O on the second theorem. Draw in chord AB for me. So anywhere you want to put a chord, go ahead, chord AB in your diagram. Chord AB. Hopefully we know what a chord is at this point now. And in the same circle, please draw a second chord, CD, that looks congruent to AB. All right, it doesn't have to be exact. All right, so please draw in a second chord, CD, that looks congruent to AB. And let's stop saying looks like. What can you put on those chords that says they're actually congruent? Your hash marks, yes. All right, so we got 2 chords, AB and CD. You've marked them congruent. Put in the hash marks on there. All right, here's what the second fact says. If the chords are equal, so are the arcs. All right, if the chords are equal, so are the arcs that they connect. So for our diagram, if this happens, the chords are equal. That tells me arc AB and arc CD are equal. Okay, chords are equal, so are the arcs. So far we have central angles equal, so are the arcs. Chords are equal, so are the arcs. No issues yet? Pretty straightforward. I'm going to show you 4. 2 down, 2 to go. Oh boy, this one's a mouthful. You don't need to draw anything here. Just take a look at this beaut. All right, if 2 chords, I draw in 2 chords, D, E, and CB. If 2 chords are the same distance from the center, and now look, I don't say the term same distance. I use that cute word up there, equidistant. All right, 2 chords, same distance from the center, those chords are equal. All right, that's what this third theorem says. Is, hey, if you got 2 chords, same distance from the center, they're going to be congruent to each other. So this one's saying, hey, chord DE would be congruent to chord CB. That's what that one's saying. Two chords equidistant from the center are congruent. All right, chords only, chords only. Two chords equidistant from the center. All right, I'm going to slow down a bit for this fourth one and get pretty fired up because this fourth one we're going to use a lot. All right, this fourth one we're going to use a lot. Circle O. Go ahead, circle O. Ho-ho! After that, diameter AB, please. Diameter AB. So circle O, diameter AB. Ready for this last part. Chord CD that's perpendicular to your diameter. I need a chord CD that is perpendicular to your diameter, please. Chord CD perpendicular to diameter AB. And if I'm asking for it to be perpendicular, after you draw the chord, what symbol are you putting on? To show me it's perpendicular, you should have a right angle symbol on there, right? So chord diameter AB, I got a chord CD that's perpendicular to it. So make sure we got our right angle symbol. Last piece I need from you guys, the intersection of the diameter and the chord, the intersection point, call E. All right, please call point E. All right, here's what happens. And you can read the theorem what happens, but if you have a diameter perpendicular to a chord, the chord gets bisected. There's a word we haven't used in a while, huh? The chord gets bisected. A diameter that's perpendicular to a chord, the chord gets bisected. So which two pieces are now congruent on my diagram? And yours too. C, E, and ED. A diameter perpendicular to a chord bisects the chord. And I'm not even done with this one yet. It is going to be rare that you guys will see the full diameter drawn in. You might see this. What's that pink piece now? That's a theorem still works because a radius is part of a diameter. Theorem still works even if it's a radius perpendicular to a chord. Now, you might see even less than what I have up here. Look. You might just see that piece. Theorem still works. Why? This pink piece up here, still part of a diameter. All right, so if it's still part of a diameter and perpendicular to a chord, the chord still gets bisected. It is, I'm telling you guys, it's going to be very rare that we see a full diameter drawn in. Most likely, you're just going to see this part. As long as it's part of a diameter, it gets bisected. All right, it gets bisected. So those are the 4 facts I got for you today. Now what we got to do is some algebra problems that use these. And yes, we're going to end going into spring break with a little proof. I know you're excited. Been waiting all day for that. All right, let's see if we can use them in these algebra problems, if you can help me out. I'm trying to find the value of x. We're not going to round to the nearest tenth. We're probably going to leave it in simplest radical form. Just so everyone knows, in this first problem, 8 is the length of the entire chord. 8 is the length of the entire chord. All right? And we're looking for that little piece x. What's happening to that chord right now? Anybody see the first fact we're going to use? What is happening to that chord that has a length of 8? Given all that information I put on that diagram, what's happening to that chord that has a length of 8? Jared, what's happening there? It's getting bisected. All right? It's getting bisected because it's perpendicular. Hey, you see what I mean? You're never going to see the full diameter. As long as it's a piece of the diameter, it still works. So now I'm going to take that 8. Yep, everyone's doing it right now. We're going to go 4 and 4. And now tell me how I can find x. Woo. Brendan, how can I find x? There you go, Pythagorean theorem. A squared plus b squared equals c squared. But I'm not using 8. I had to know that theorem to get 4. Somebody plug in for A, B, and C for me now. Whew. Lily, what's A and B? X and 4. Good job. X squared plus 4 squared. That leaves 5 for my hypotenuse. Good work. Everyone go ahead and solve. Make sure you take the square root at the end. And when you have X, let me know. Whew, there we go. Vinny, what do you got over there, boss? 3. Good work. All right, good job solving algebraically. Now I want to know what would go in our reasons column for a proof. All right. What did we use to bisect it? Here we go. Diameter. What do I have to know about that diameter in the chord? They have to be perpendicular. Diameter perpendicular to a chord. What happens to it? Bisects the chord. There you go. This is what I would be writing in a reasons column of a proof. Diameter perpendicular to a chord bisects the chord. Any questions using this theorem? Woo! Next one. Next one. What do I got going on there to find chord X? Nothing's getting bisected here, right? There's no diameter perpendicular here. Nothing's getting bisected. But I do have to find X somehow. And I know you guys are looking back, searching for the 4 facts we did today, but none of those 4 are going to help you here. We got to go to the entire circle unit and everything you know. All right, I am not using one of those 4 facts here. I'll give that to you as a hint. I need something else we've talked about in the last few days that you can add to your diagram here that you know is true. Anybody adding anything to the diagram? Selma, what are you adding?
6.
6. Yeah, whoa, that's a radius. Any other radius in this darn diagram will be 6, including this missing one. That's 6. Now what can I do to find X? Whew, got enough information here. Dylan, great talk. Good work. Let's go up to Micaiah. What can I do here? Pythag, good. Plug in everything that needs to be plugged in for me here. Going back, Lily, what's got to be plugged in? Good work. Leave it in simplest radical form. I don't want nearest 10th. Just your calculator leaves it in simplest radical form, so do that for me. Simplest radical form, what do you got for me? 1-7, Dylan, excellent job again. Jared, back to you. 6 radical 2, thank you. Over here, what do we use? We didn't use any of the fancy ones from today. We put a 6 on there, why? False. In life, yeah, darn right, Lily, not in life, but in a circle, all radii congruent. All right, let's go. Let's go. 5. Next one, it's not 5, it's 3 for you guys. Ooh, there's a lot going on there, huh? All right, there's 2 things I need for this one, but what's going on in this circle that you know is true? I'll start anywhere. What's going on in this circle that you know is true? What do you have? Radii. I don't see any radii. I see part of a radii. Not a full one, though. Some chords are getting bisected, aren't they? Right? Because I have part of a diameter that's perpendicular. So both chords are getting bisected. True. I'm going to use that next, though. All right, I need one more fact here. Yes, everyone agrees the chords are getting bisected. So if anybody could find me the length of this one, I'll bisect it and find X. But I need help finding the length of that chord. What do you got over there, boss?
They're the same distance.
Oh! Both chords are 7 units away from the center. If two chords are the same distance away from the center, they are congruent to each other, because if they're equidistant, they're congruent. So here's my first thing. The chord, watch, the chord I know is equal to 6. Everyone agrees? This chord here is equal to 6 because it's equidistant from the center. And where else? Who else told me the bisecting part here? And it's getting bisected now. So x is going to be equal to, I know it's easy math, but it's the theorems that count for me. You take that chord of 6 and bisect it. So x equals 3. All right, we use 2 theorems here. First theorem, how do we get the chord of 6 again? Ready? Chords. What do we know about these chords? Chords equidistant. Keep going from where? From the center are congruent. That's how we got that other chord to be 6 units long, because they're equidistant. That's how I know that other chord is 6. And then how'd I go from 6 to 3? Diameter. Second time we've done this now. What do we know about that? I know it's not a full diameter, but we just write the word diameter. What do you know about it? Perpendicular to a chord bisects the chord. I know the math is easy there, but it's the theorems that I want to get through. So these haven't been too bad. All right, here you go. Now I'm really going to go up a level here with this last algebra problem. All right, I'm going to step up the game a little bit here. Find x. And that's the whole chord. What is the length of that whole chord there? All right, anything going on that you're confident in this diagram? What's going on? Chord's getting bisected. Everyone agree? The chord's getting bisected. So if you guys could help me find maybe half of the chord length, I could double it at the end, but I still need help doing that. I know the chord's getting bisected. All right, great. How do I find half of it, though? You know, to get it, double it. I don't want to give anything away here. I want you guys to think where I could go next. Any help, thoughts here? What do you want me to do for this diagram? Because you're absolutely right. The chord's getting that's going to come into play. The chord is getting bisected, but not right now. We need to find half the chord so I can double it. How do I get to that point? And everything's up there for a reason. I'm not trying to throw you off by anything. But I want to try anything, throw anything out there. How you can find that chord length. Go ahead, what do you got over there at that table?
The diameter is 6, so you can extend the radius to like the whole diameter.
That's a radius up there I labeled 3. Everyone, right? 3? If you draw in any other radius in that diagram, how long is it going to be? 3. And why am I saying draw in another radius? Isn't there going to be a convenient one that's going to form a right triangle for me? Yeah! Yep. Take a look right here. You want to draw it this way. Some of you could maybe draw it that way too. It doesn't matter which radius you draw in. They're all going to be 3. Now what can I use to find half that chord length? Now that I drew in that extra radius for me, that helps me out. What can I do to find the other chord length here? Hey, Lily, you're on fire today. Multiply. Well, we need to multiply this part by 2, but I need to find that part. Pythag. There you go. That's what I'm looking for. Good. And could somebody plug the 2 and the 3 in where they need to go into Pythagorean theorem for me? Oh, there we go. Tess, what's Pythag looking like?
X squared plus 2 squared is equal to 3 squared.
Good job. Yep. 2 squared. I'm going to leave the x out just so people know I'm not solving for that x I'm looking for, so I'll keep it b equals 3 squared. Yep. Keep everything in radical form for me, kids. And what are we getting? That half of it to be square root of 5, right? Half of it is square root of 5. And we said, all right, it's being bisected, so double it. So x, according hopefully on your calculator, is 2 radical 5. The length of that chord. Yeah, so add in your own stuff if you have to. Draw in your own stuff, especially radii. Whoa, whoa, what did we use here? I think we used 2 circle facts, didn't we? What did we use here? What's one fact that we used to get to the whole length of the whole chord here? Yep, good talk. Let's go 1-5. Alexi, what's one theorem we used here? That's not Pythagorean theorem. A circle fact that we used to get to 2 radical 5. How do we get to 3? Why did I write a 3? How did I know that piece up there that I wrote in was 3? Thank you. In a circle, all radii are congruent. And then second, how did I know to not keep radical 5 as my answer? And how did I know to double it? Right? How did I know to double radical 5 and just not keep it? Stephanie, over to you. What was happening to that chord? Yep, it was being cut in half. How do I know it's being cut in half? Because you had a diameter that was what? It was being cut in half, and I'll get to that in a second. But why was it being cut in half? Because you had a part of a diameter that is formed a right angle. Diameter perpendicular to a what? What was it perpendicular to? A chord, yep. Now go ahead and finish it. What happens to the chord? There you go. Diameter perpendicular to a chord bisects the chord. You got it. And this is the exact wording I'm going to see in a proof when we get to them after break. Any issues here? Speaking of going into break, why not we end it in style? Here we go. Yep. Yep. Everyone ready? Not even slow clap. Okay, you got it. Prove angle A congruent to angle C. Notice what I gave you though. B is the midpoint of arc AC. Hey, midpoints work the same way we've been using them all year long. Tell me what's true now then. If B is the midpoint of arc AC, midpoints are working the same way, guys. They've worked all year. What's true now then? If B is the midpoint of arc AC, what do you got for me? What's got to be true then? Going deep, Brendan, over to you.
CB congruent to AB.
The arcs, right? The arcs. Now, I'm not, when you say CB and AB, I'm not talking about these. I'm talking about the arcs, right? Are congruent? Yeah, it works the same way. Midpoints, cut it into 2 equal parts. And why don't we throw that into statement 2 so we don't forget about it, right? Sometimes we mark our diagram and we forget to put it in the statements. Arc AB is congruent to arc CB. And the reason isn't changing either. What would we usually put? What would go here? Usually we do it for segments, but now we're doing it for arcs. Right? Definition of midpoint. Okay, you guys know what I'm going to say here. We are not going to get angle A congruent to angle C in this diagram unless what first? The darn triangles are, correct. So get me the triangles congruent. Anything you know that's congruent up here. Come on, let's roll. Give me something that's congruent up here. Tess, let's roll. QB in itself. All right, let's start there. QB, congruent to itself. The old reflexive for us. Got it. Well, I should probably do what I used to do in the past just to be consistent. All right, Tess got us aside. Zoli, where do you want to get us? Correct, because they're both what? Good. Now, hey, I don't know if anybody's going to do this. This came up first period. You cannot say in the same statement that QA, QB, and QC are all equal because they're radii. You have to say QA and QC separately because those are the sides that match up. And you have to say QB and QB separately because those are the sides that match up. You can't say all three together. You got to give me the pairs of sides that match up. So yes, QA congruent to QC in a circle. Got to have that piece, right? In a circle, all radii congruent. Period 2 on fire here. Looks like I need one more piece of congruent parts here to finish this. Oh, let's go, Cork. What do you got for your crew here?
CB congruent to AB.
Ooh, were you going to say that, Simon, or are you going to say something different? Good, save it, because you're going to be correct. Let me just go with Cormac's here, which is line. Well, actually, I don't want to call it line segment AB. What is that in the circle he's telling us? AB is what? Chord. BC is a chord, all right? And we'll talk about why they're congruent. AB congruent to chord CB. This was one of our theorems today, and I don't want you to write the whole thing that was in the box. How'd you know they were congruent? Because what were congruent? Okay, everyone ready? Congruent arcs, that's what was congruent, implies, what did Cormac just tell us were equal? The chords, right? Congruent arcs imply congruent chords. I got enough to say the triangles are congruent? Darn right. Here we go. Make sure, again, the sides stay in order. Triangle AQB congruent to triangle CQB. Reason? Side, side, side. Not a big deal on that one. And we needed the triangles to congruent to say the angles A and C were congruent. What's that reason? All right, hold on. I'm not ready. I'm not done yet. Not done yet. I want to get Simon his glory here. All right, I ended up calling on Cormac first, and he gave me the chords. What were you going to say instead were congruent, Simon? Hey, what type of angles are these right here, everybody? Congruent arcs imply congruent central angles. We could have done that and then done side angle side. Okay, so that would have been congruent arcs imply congruent central angles if you need those. All right, so that could have been another way and do side angle side.